Welcome everyone to Coffee with Caleffi. Today we've got a really cool topic. This is a tool that we've loved at Caleffi for a long time, as long as the water demand calculator has been out. We've thought, hey, this seems like it's a good modern tool. We'd like to learn more about it. So as this tool has grown, we wanted to kind of have the IAPMO team back on to give us an update for things that they've done, some research, some background information, and where this tool is headed next. So that's kind of the general topic today, and we're going to hear right from the experts. So I'll go through a couple intro slides here, and then we'll turn it over to the team. So if you are having audio issues, best case scenario is just close GoToWebinar and come back in. If you want a copy of the presentation, hit yes in the post-webinar survey, and we'll send that to you in an email. And then we'll also put this up on YouTube later today and get that out to everybody in case you have a colleague who missed it, or you want to go back and reference something that you wanted to see in a little bit slower presentation or something, that you can pause it. And then certificate of attendance. So check your email. We'll send you a certificate. It depends on your jurisdiction if you're allowed to submit these, but it'll have all the course information, date, and the things that they usually require. Hydronics 35 is out now. We're actually just looking at the Hydronics 36 kind of second draft now. That's going to be a topic on zoning, which will be something that we haven't talked about in about 10 years. Currently, we have an evaluating hydronic heating circuits topic that's up now, so you can see that on hydronics.caleffi.com, or you can sign up to get a hard copy in the mail. Same website, you can sign up for the postal delivery there. And then next month, we're going to go back to a hydronics topic. So this is going to be kind of a pre-heating season topic to make sure that you're taking a look at some of the things that are very much an inconvenience if they break the first day that it snows in the winter is kind of the working topic that we have there. So Dan Hilligus is going to present that one, and we're excited to kind of hear, he's a manufacturer's rep from the field, what are some of the common things to just do in July instead of waiting until November or October whenever it gets cold. And then one of the things that we wanted to mention, and the presenters are going to get into a little bit more detail with the other kind of charity related topics, is this iWish Foundation. So this is something that's a cool outreach program that IAPMO is coordinating. We actually just contributed some valves to, it's called the iWish Community Plumbing Challenge in Navajo Nation. So we sent some mixing valves and balancing valves to this project to kind of help give back to the community a little bit, but really well organized, really cool foundation that they have there. And then with the next slide, I'm going to bring our panelists onto the call. So please welcome Christoph Lohr. He's the IAPMO Vice President of Technical Services and Research, and Toju Omaghomi. She's the IAPMO Industry Research Manager. So these are the water demand calculator experts. I'll let them kind of take over with the content here. I'll keep an eye on the chat if there's anything that would be important to relay, but take it away, team.
Excellent. Well, Max, thank you so much for the kind introduction. I'd be remiss if I didn't also add that we have actually a new fund as well, our Innovation and Research Fund, that's part of IAPMO's efforts to really push forward even more than what we've done. So in addition to the water demand calculator research that Toju is going to go in towards the end of our presentation today, it's a new vehicle for us to do great work in terms of plumbing research, especially around the topics of water and drainage and storm systems and whatnot. There's a QR code, and just for everyone's knowledge, there's a number of QR codes, so have your phones ready. We'll try to give everybody a chance to check out those websites as we go through. I think, Max, you're going to also try to drop some of the links in the chat as well for those of you that don't have ready access with your phone. But if you have questions or if you want to see one of those slides again, we definitely would be happy to bring those up as we get towards the tail end of our presentation as well. So with that, the topic today is the water demand calculator for hot water systems, some basics on how to use it. Myself, Christoph Lohr, I'm IAPMO's Vice President of Technical Services and Research, head up our Technical Services and Research team. And I have the distinct pleasure of working with two just fantastic individuals, Toju Omaghomi, who's a PhD researcher from the University of Cincinnati, who IAPMO is now an IAPMO staff member. She's our manager of industry research. And then Dan Cole, who was really the catalyst behind creating the water demand calculator. Unfortunately, Dan is not able to join us today. We were hoping that it would work out, but he is actually attending the We Stand technical committee meetings. And the We Stand is actually one topic that maybe some of you folks haven't heard of before. It really is. It's a very remarkable ANSI standard that IAPMO develops, a bit of a stretch code, if you will, that really tries to provide requirements to optimize water use practices while maintaining protection of public health, safety, and welfare. So that's right in the purpose of the document. One of the things I've really loved about We Stand, I think from the engineering standpoint, is I see the opportunities to put this as there's lots of things about water reuse, the water demand calculator, hot water ratios, leak detection devices, and a plethora of other topics around water use. And it's a really wonderful topic because it really balances well the public health and safety and the efficiency of water use in buildings. So sometimes we've had situations where standards have come out as an industry that have promoted practices perhaps that haven't led to safety, while trying to optimize water use or energy usage. And this is really one of those documents that just, as I've come to spend the time here in my last almost 5 years at IAPMO, I have learned about this. If you're not familiar with it, highly recommend you guys go check it out. Max, thank you for putting that link in the chat. So we'll just be Toju and I today. Here's a rough introduction or rough objectives that we have. So we're going to spend a little bit of time on the introduction to the water demand calculator. How can design professionals use the water demand calculator, showing some of the results. And again, we're going to do a very high level today. So this is going to be a bit of a quick breeze through. If you want another topic, I think one of the things that Max and I, along with Toju, what we coordinated was maybe doing a poll by the end or doing a polling throughout. If you guys want us to do a deeper dive into something, we would love to come back and do that for you all. So if there's something specific that you want us to get into or suggestions, we would love to hear it. So after going through some of the high level stuff, Toju is going to spend some time on the confidence level. One of the big things that a lot of engineers seem to have a question about when I presented, or Toju's presented, or Dan's presented, is what's the confidence level that we can have that the water demand calculator, won't undersize, with right sizing. That's a really key one. And so Toju's going to spend some time on that, and then we're going to jump back into the benefits specifically as it relates to hot water systems. So just worth noting, IAPMO, we can't endorse or recommend any particular product, but we're here just to provide information. So this is nothing specific for any particular manufacturer, but just here to provide education. And then finally, the future. I think a lot of you folks that are here today, you're excited to hear about what the future is. We're doing a lot. We have some really exciting pieces here coming up, and really excited to share some of that with you, at least giving you a glimpse of some of it and the ways that you can learn more about it. And then any additional resources if we have some time at the end. If you guys want to learn more, we're going to give you lots of QR codes at the end here and websites. So definitely stay tuned for that towards the end of the webinar here. So let's touch base first on the introduction to the water demand calculator. And really what that comes from is a question that Dan Cole asked very early on, which is, what is the problem with the Hunter's curve? So really what we're going towards is, even though the Hunter's curve has adjusted fixture, some of the flow rates, some of the fixture unit values down because of more efficient water fixtures, the problem is that there's the fixture unit has two criteria inside that number of the fixture unit. One is the flow rate of an individual fixture, but the other one is that it's a probability of simultaneous use. And really what it boils down to is that we're using something from the 1940s that assumes every home operates like a sports stadium at halftime. So let's dive into that a little bit. So again, Roy Hunter was commissioned by the U.S. Department of Commerce back in the 1940s to develop a way to size piping systems, a more standardized unit. What he came out with was BMS 65. Many of you have probably heard of that. And that particular report is what we basically used as an industry ever since 1940. Now, Dr. Roy Hunter had he had very limited, some very limited means compared to present day in terms of what he could do in terms of estimating peak flow rates. First off, we have to recognize he did not have a computer, let alone a calculator, to do any of the calculations with. He had a slide rule. And the other part is he had very limited data, and he had to make some assumptions to make the mathematics a little bit easier in terms of statistics and probabilities. And that's all the information in terms of statistics and probabilities. Why I'm so glad Toju's here. She can definitely provide a lot more context to those questions if you have them. So put those in the chat now, and then we'll want to make sure to address those later on. What it comes down to when we talk about simultaneous use. So if you're looking at this bank of laboratories here, let's pick on that lavatory right there at the one closest to us, you know, in the image. Imagine I'm there washing my hands and you know, doing my thing there to make sure my hands are clean, and I step away, and then Toju steps right in after I leave to start washing her hands, and then she steps away, and then Max comes in and start washing his hands, and he steps away. That is a long queuing line for a certain plumbing fixture. And when we talk about, you know, that sports stadium like usage, imagine that type of queuing line at all of these lavatories, at every water closet, at every shower, at every bathtub, at every single plumbing fixture for a whole building. That is the simultaneous use, that likelihood of having the pulses from each fixture occurring simultaneously, that the peak flow rate is what we're estimating the sizing for any particular building. Now, obviously, that kind of a line really only happens in you know, assembly type occupancies. So what we're talking about is airports, you know, maybe when they come in, sports stadiums, most certainly at halftime, you know, an opera house or a movie theater, you know, at intermission. You're talking about congested use. But you know, Dr. Roy Hunter, he made that assumption for all buildings because he didn't have the data. You know, and he had very limited means to making that calculation. And really, after he died in 1945, that whole program kind of went by the wayside, and that's what we've just used for the last 95 years. Fast forward till today, you know, and back in the early 2010s, Dan Kolb had that question, like, that doesn't seem to make sense when he started diving into it. And the thing that's remarkable about Dan, he was a plumbing inspector that went back to a community college to take courses in statistics, probabilities. I mean, just remarkable. I feel so privileged to work with Dan and get that opportunity to learn from him on how some of the stuff works. Because of Dan's interest in that, in a paper he presented at the World Plumbing Council, at one of the events there, I think maybe even at the Emerging Water Technology Symposium that IAPMO and other co-conveners like ASPE and others put together. He was hired by IAPMO, and then he convened a group of a task force to start looking at this, which included the American Society of Plumbing Engineers, and then also the University of Cincinnati, which at the time Professor Stephen Buchberger was the professor there, and had Toju Omaghomi working with him on the development of the Water Demand Calculator, which was ultimately released in the 2017 WESTAN, which I mentioned before, and then the 2018 Uniform Plumbing Code in Appendix M. And that's where we have this new way of sizing or estimating peak flow rates, which can be used to size a pipe. So let's touch base real quick and just make a quick clarifier. The water demand calculator doesn't size a pipe directly. However, there are two main criteria when you size a supply pipe in a plumbing system. That is the available pressure, which is obviously independent of the peak flow rate, and then the peak flow rate. That's what we use as a plumbing industry. We're not using generally average volumes or other things. We need to know what that 99th percentile peak flow rate is. And again, Toju can give you a bit more detail on that, especially during the Q&A section. So when you look at the water demand calculator, again, it exists in two particular standards. One is the IAPMO ANSI standard WESTAN, which is now ongoing into the 2026 edition, and the other is the Uniform Plumbing Code, which we are just finishing up the 2027 Uniform Plumbing Code, which it still exists there in Appendix M. Also worth noting is that with these standards, there's a separate Appendix M adoption, which some states like Wisconsin has done as well. Right now, the water demand calculator has been adopted in at least 10 states. There's 2 more states that have already approved it, but it's not going to go into effect until later this year. And then we have a smattering of other cities and jurisdictions that have adopted it, and some states, some cities have started to mandate the use of the water demand calculator, which is rather interesting. Worth noting, just like other codes and standards, the water demand calculator is a free download. So if you go to this website, there is a free version of the calculator. There will always be a free version of the calculator. In Excel, you do have to enable macros, but it's free and free to use. So we have some pretty detailed instructions in there. Again, if you need to work with your IT to get the macros to work, please do. But once you have that version, it's pretty straightforward to use. So just some quick features and functions. And again, that QR code will take you to the website to download the water demand calculator, and has a host of other resources around the water demand calculator. First off, make sure you're using the latest version, 2.2. We have a project name and then a drop-down menu, which I'll address here in just a moment. It will show the date that you ran your calculation, your fixture groups, which includes bathroom fixtures, kitchen fixtures, laundry room fixtures, bar prep fixtures, and then other. Then you have your individual fixture types, which are listed as such in each of those groupings. You enter your total number of fixtures. So again, the white cells are cells that you can go ahead and modify or edit, if you will. You have a probability of use, which remains unchanged, or that's automatically done, especially for the multifamily that shows up there. If you're doing an other fixture, you can pull from the probability from up above. And then you have a fixture flow rate, GPM, that you can modify. Now you can't, at the current time, you can't go above the fixtures because the water demand calculator was utilized for high efficiency fixtures as part of WeStand. However, we do have a committee that's looking at potentially and considering elevating those peak flow rates for future versions of the water demand calculator. So stay tuned on that. And then again, this last row is just a reference row in terms of what the maximum fixtures are. Here's where your outputs occur, including your total number of fixtures in your calculation, what your 99th percentile demand flow is. So that shows up right there. Your Hunter number, which is a reference back to some of the Hunter's curve pieces. That stagnation probability is a wonderful number that Professor Steve Buckberger and Toju Omaghomi came up with, especially in this age where we have to consider water age and water quality and water management. That's a good number to kind of look at. And then the method of computation. There's 3 phases that the water demand calculator goes to. I'm not going to get into that too much today, but that's just worth noting which version it goes into. And then the green button. Once you put all your inputs in, you press that green button and that gets you your outputs. You do have choices in units, which you want to select. And then your download results, which is either a note file. You could also copy and paste the results in as well via Excel into Revit. I think I've spoken with engineers, and having been an engineer, could go either way, shape or form. Now, worth noting, again, there is the single family. There's a drop-down menu there that's highlighted in red. If you're going to do multifamily and you're doing a line coming into like an apartment complex or condo, when you drop down and select the multifamily, what you will see here is you have to include the total number of apartments in the building and then the total number of apartments in that particular running of that calculation. That's vital because what happens is it changes actually that probability of use. One of the things that Toju and Dan discovered when they were starting to look at the at multiple dwelling units is that the more dwelling units you have, the likelihood of simultaneous use goes down. So for larger buildings that have multiple apartments, you're going to actually start seeing a lower flow rate output for more dwelling units when those bathroom groups are split up into different dwelling units. And that's a key function here. And that's really where that behavioral pattern of one home to another really starts getting shifted. Max, I just saw, I think, a hand raised. I'm not sure. Do we want to do questions at the end, or do we want to do them during through?
Yeah, we can do them at the end. And if you want to type in if you have a question that pertains to a slide, the easiest way to relay that is to type it into the chat, and I'll see if I can keep up with those. Or we'll get back to everybody if we don't get to a bunch of questions by the end.
Perfect. So just a real quick summary. Again, we had to kind of condense it for the purposes of this presentation. So the first thing when it comes to using the water demand calculator, you have to recognize that the water demand calculator, as it currently is, only applies to residential buildings. Now that can be single family or multifamily. If you have a space that's like a mixed use building where you have, let's say, shops on the bottom and apartments on top, you can use the water demand calculator for the apartments at top, for those areas downstream. However, for, let's say, your combined water service entrance coming in that's feeding both, what you'll want to do is take your water demand calculator for your residential occupancies, and then you use the Hunter's curve for your commercial spaces, and you add those numbers determined independently together to come up with your total flow rate for the combined water serving both mixed use and the multifamily. We are working on retail spaces though too, so hopefully soon we'll have a way to just package it all up in the water demand calculator, but it's going to take some time. But more on that later. Again, you need to have water conserving fixtures. Again, riser diagrams showing the pipe segments. Highly recommend doing that riser diagram to show your peak flow rates for segment by segment. And then it's just following Appendix A from the UPC, which is the longest length method. So you do your friction loss calculations based on your available pressure and longest length. So you get a PSI per 100 lineal feet. You do your pipe sizing chart, and then you just plug in that water demand calculator demand based on what your available flow rate is for your pressure loss PSI per 100 lineal feet. And then that helps you, that gets you to select your pipe sizes. So if we're going to show a quick example of what some of those, how that works, if we're doing a pipe sizing method for, let's say, hot water, again, in this particular case, utilizing a pressure drop, I think this one's about 15 PSI per 100 lineal feet. Utilizing the charts in Appendix A, what you'll see is that a half-inch line has a maximum hot water demand GPM of 3.5 GPM. Again, you're lowering that feet per second down due to velocity limitations of copper in this case. 3/4 inches goes up to 7.5, 1 inch goes to 13 GPM, and 1 1/4 inch goes down to 19 GPM. So when you're sizing your hot water supply coming out of the water heater, you would just put in those flow rates for each one of the segments of pipe, and then you'd go back and refer to the chart to come up with your size. So for pipe segment 1, in this case, the one that is, let's see here, for coming out of or let me see, that's, yeah, pipe segment 1, which is combined, the combined main serving the lavatory and then the tub and shower. You have 7 GPM, so that's a 3/4 inch. Going back a little bit further, that combined main where for that bathroom plus the clothes washer, or excuse me, not the clothes washer, the kitchen sink, that the water demand calculator estimated at 7.7 GPM, so that equates to a 1 inch in this particular example. And then going back a little bit further, getting closer to the water heater, you have the clothes washer there, that gets you a GPM of 9. That pipe size, the hot water pipe size, would be 1 inch. So that's, again, just looking at that chart that we created from before, and then what the water demand calculator creates for each one of them. Now, when you have just an individual dwelling unit or single family home, typically the pipe sizes are mimicking pretty closely to what the Hunter's curve does. But when you start scaling up and you're getting a multifamily, what you'll notice is that you're going to see reductions in pipe size. So this is a particular example. That QR code takes you to a YouTube video. Our colleague, Randy Lorge, who's a master plumber out of Wisconsin, he did this for our IAPMO San Antonio conference in 2023. We got a recording of it. He goes through and breaks this down for a whole specific multifamily application for cold and hot water. But looking at the pipe segments 12 through 20, which is just the hot water side, when you start looking at the total potential simultaneous use for each segment of pipe, what you'll notice is table 610 and appendix A by itself, which basically falls on the Hunter's curve sizing, estimated a 1 1/4 inch line coming out of it that was necessary. The water demand calculator only required a 1 inch line. So generally speaking, when you're doing multifamily, what you're going to see is that like 95, 99% of the time that the peak flow rate that the water demand calculator comes out with is going to be lower than the Hunter's curve. Sometimes you get a little bit of an anomaly here where the water demand calculator is slightly larger. But again, generally speaking, you're going to be you're going to be smaller. Where you really see this, let's say you have a 100 unit apartment complex, the hot water, like the cold water line coming in may go from a 4 inch down to a 2 inch. So let's say your hot water was a 3 inch makeup to the water heaters, you might be able to get away with a 2 inch or 1.5 inches. So as you scale up, like if you have a central hot water system, that overall pipe size is going to go down. We'll touch on the benefits of that in just a moment, but I'm going to turn this over now to my colleague Toju to talk about some of the confidence level, because this is a question that comes up typically. So Toju, if you want to go ahead.
Thank you very much, Christoph. So everybody knows about Hunter's curve, and then we come out with this water demand calculator, and it's not a simple plot. Everybody was asking, why don't we just have a straight line? Well, we can't have a straight line because we found out that depending on the size of the building, it requires a different method and it requires different parameters. And so they are concerned because we now have these very small numbers, and they're like, how did we get it? Next slide. So what went into the water demand calculator was data from over 1,000 residential buildings, and where it was across 9 states, 62 cities. And what we did was look at where and when water is being used in these homes. So the data told us that at 7:30, the faucet is on, the shower is on, the toilet is on. And so we can see what is happening at the individual fixtures and for how long these fixtures were used. And so we were able to calculate the probability that water is flowing at the individual fixtures. We also use the same data to assume that each residential building is a unit in a multi-apartment building, and we found out that as the number of units increases, the probability of peak hour use for these fixtures reduce, because not all of the homes are in simultaneous use at the same time, as we will have in a stadium or when everybody's using the fixtures at the same time. Next. And so what happens is when you look at measured data, and this is from 20 different multi-apartment buildings. This is for hot water use, and compare it to the result that you would have gotten from Hunter's curve, which is the red line you see there. You can see there is a great difference. And when you zoom in, so the plot on the lower left-hand corner is the lower end, looking at that green insert there, you see that these buildings have really low water use, and this is specifically for hot water. And sometimes these design numbers are up to 27 times larger than what we're seeing being used in the building. And there's a whole lot of problems with oversizing your system, which Christoph might get to, but we're just looking at the specifics. Next. Now, in this plot, we will compare what is being measured, what it was designed for, which is the red, to the water demand calculator, which is the blue. So what was measured is the black. The highest we see is about 20 GPM from a building with 384 units. And we can see that the water demand calculator is at least close to reality compared to the red lines, which is what they would have used to design the system. And I can also tell you that depending as the size of the building increases, the increase in this difference is what we are noticing here too. That's why you can see at the end, you see all the last 4 buildings, they could not even put the data point for the design on the plot because it was way out of range. Next slide. When we're looking at the same information, next slide. But this is in tabular form. And you can see that no, go back.
Sorry, Toju, I went one too far.
Yes, so we're looking at the same information, but it's in tabular form. And you can see that the water demand calculator, which is the Appendix M design here, is minimum between 2 times to 6 times greater than what was being measured. But if we were looking at the water supply fixture units method, is between 5 times to 27 times more. And I want to draw your attention to also the time of zero flow, because when we have these residential buildings, most of the time people come and go, and there's a whole lot of times there's zero flow in the building. But as you see, if we go to building P, which is Seattle 384 units, you can see that that was the building with the least probability of zero flow. And that's because when we have all these units, there's a whole lot of things going on in the building. There are very few times water is not in use, even during the peak hour. And just that's for us to know, because Christoph mentioned probability of stagnation, which is one of the results the water demand calculator gives you. Next. Now, this result we just shared, is what went into California adopting the water demand calculator for their energy codes. And you can access the reports and everything about it, because we just showed you one table. There's a whole lot that went into it, looking at the 20 buildings and everything that happened in them. So you can scan the QR code or the link to access the report.
Definitely. And just want to add, Toju, this particular report was really well done by 2050 partners, Gary Klein, and a number of other folks, the Association for Energy Affordability in California. So just a big kudos to them for putting this whole thing together. That's a free download. Go ahead, Toju.
Okay. Next. Now, this is an example of the kind of data we're looking at now. And I'm just showing you this so that you have an idea of how the system is greatly oversized. This is an 18-unit condo, and just for 2 days so that we can zoom into what's happening. And we can see the pulses around midnight and noon for irrigation, right? But if we just size for this building alone, the water demand calculator will give you 18.7 GPM, but we can't, and then you add the flow for the irrigation and the pool, which will be 60 something. And we can see that that's the maximum recorded, but the system was designed for 153 GPM, which gives you 2 times larger main size and meter size than you required. Next. Just to see it in a different way, if we're looking at the distribution of flow for that particular building. So now I'm looking at the entire data. Data was collected over 30 days. 50% of the data, about 50%, were zero flows. And that is when nothing is moving in the pipes. And by the time we get to 90%, we're just at 5 GPM. So everything happening in the building above 5 GPM is happening less than 10% of the time, and we're not seeing the kind of flows you're necessarily designing for. And so that is why the water demand calculator came in, because we need to be sizing the systems rightly so that we can have the benefits of water conservation, energy conservation, and other things. And Christoph, next.
Definitely. So I think Toju did a great job summarizing the overall confidence level that engineers can have with the water demand calculator. And I think just to hone in on just one part of what Toju presented, the water demand calculator always, in essence, estimated underneath what the Hunter's curve would estimate, that the fixture unit method, sometimes by a factor of as much as 10 times, but it was always still at least a 2 times safety factor from what the actual flow rate was to what the water demand calculator estimated the peak flow rate to be. And that's really vital. And that speaks to the good work that Dan, Professor Stephen Buckberger, and Toju all did when it came to the thoughtfulness put behind this to make sure that we're not going to end up in a situation where a system is undersized. Again, we call it right sizing because, again, we're getting closer to what the true peak flow rates are, but we do not want to be underneath it. And that's really a vital piece of the thoughtfulness that's put into this, just to make sure that the system is operating efficiently as best as we can. Now, when it comes to right sizing, especially in the realm of hot water, we have some really great potential for benefits that come from this approach. So first off, just worth mentioning is the Stantec report. IAPMO, we commissioned Stantec back in around 2020, 2021. We have a free report that's accessible from that previous link to the water demand calculator that I showed. And this particular report, the Stantec report, looked at the construction cost savings. Now it looked at hot and cold, but you can definitely derive what the hot water savings would be by lowering an individual dwelling unit basis. And that particular report on the construction cost savings looked at multiple markets. So high construction cost markets to low construction cost markets, in terms of size of the cities of those markets, and looked at different types of single family, and multifamily applications. I think for this audience, probably the multifamily numbers are going to be definitely of interest. And again, this assumed individual water heaters, I do believe, per unit, not a centralized hot water system, which those savings could be much larger too. It's not unheard of for a multifamily, for 6-figure, especially if you're having like hundreds of units of apartments, having 6 figures or more in terms of overall pipe material savings. So that's a great opportunity to really have a positive impact by utilizing this. Now, the other report that's worth mentioning, the other approach is the sustainability savings. When you look at water savings that come from right sizing, the big one that we like to focus in on is the elimination of structural water waste. Now, there have been some folks out there that question this, and some entities that have said, well, is there any water savings that are actually capable of this? Well, yes, there's actually at least 24 peer-reviewed studies out there that we have listed on a sort of separate subpage of the Water Demand Calculator webpage I mentioned to before. This is the link that'll take you there. And this one particularly, looks at those benefits of structural water savings. Now, if you're not familiar with structural water savings, that image in the bottom left is a summary from a presentation done at the ACEEE Hot Water Forum by a gentleman by the name of Jim Lutz, who's a longtime ASHRAE member, and he did a study of showers that looked at behavioral and structural water waste. So structural water waste was basically defined as if that pipe going from your water heater to your fixtures, so lots of hot water fixtures, if that was reduced, let's say 1 nominal pipe size, there's a difference. So for example, let's say you had a 3/4 inch hot water makeup going to serve your hot water system, and you reduced it to a 1/2 inch, let's say, based on the example, whatever numbers work towards that. There's a difference in volume that you don't have to account there's a difference in volume that if it was captured every single time you activated your shower, that that could lead itself to potential savings. To put it in another way, most of us hopefully showered this morning or last night. And for the most part, if I were to ask, I think most people, how long do they wait for their hot water to go to appear at their shower? It's usually a matter of a few minutes. That's because that hot water at your home that was sitting in that hot water piping cooled off overnight. And so you have to open the shower and basically flush out that cooled off hot water with actual hot water from your hot water source. Now, some of the folks that say, well, I turn on my shower and I jump right in because there's hot water right there. Usually it's a combination or due to things such as the water heater being right on the other side of the wall, or they have a recirculation loop at their home or apartment that's very close to their shower usage. So those kind of things can have an impact. That's kind of one of those things of structural water waste. It's length and diameter, right? That's the total volume. However, if I ask those folks, well, did you ever live in a house that wasn't right on the other side? They all they all say yes, and they all say, well, we waited a few minutes. So that's what we're talking about with structural water waste. So the diameter with what the water demand calculator calculates is a key component of this. If you were to calculate in single family homes or multifamily dwellings where let's say you even bring that hot water source through a recirculation loop pretty close to the shower, IAPMO, we commissioned ARIP, and then there's been a number of other studies done as well. And you start comparing the numbers for each one of them, the potential savings is around 500 gallons per year per dwelling unit is what everybody kind of revolves around. So what that means is just by right sizing, inside the dwelling unit, your hot water systems, the potential for savings equals an outdoor hot tub worth of water saved every year just by not having that much water going down the drain. So there's certainly more things that you can do, but that's 3 different studies that have all kind of started coalescing around similar numbers. The other thing worth noting, though, is that those numbers are based on only needing to displace 100% of that volume difference. What real-world studies and research is finding, like such that Gary Klein has indicated, is that the actual value of volume displaced is somewhere in the range of 1.5 to 2.2 times that volume. So roughly around 2 times. So in essence, what happens is as that pipe cools off and you start introducing hot water to it, that cooled off pipe material actually decreases the temperature of the hot water coming through it as well. So some of these numbers could actually be on the lower end of the spectrum. So just worth noting that here, that there is a lot of potential in this realm of structural water waste that we're reviewing, and that's included in these numbers. But again, 3 different reports, which are all summarized there, all kind of ended up in a similar piece. And again, the reports are also looking at the 3 different folks like Stantec report that we had, and then these other reports. They're all estimating somewhere in the range of $500 to $2,000 in pipe material savings per unit as well. So lots of potential there. The California Energy Code, they looked at this, quite a bit, and they looked at the water savings, but they also included energy savings from right sizing. Again, there's a water energy nexus. It takes a certain amount of energy to deliver the hot water from the building, from the water purveyor, to use. So by right sizing, you're saving some of that energy as well. These reports indicated that. And the other piece that's really unique here is that this is one of the few instances where a sustainability benefit doesn't cost more at the start. It actually costs less. So you get some funny results like from the report I've been referencing here from the California Energy Commission. The benefit cost ratio is infinite because we're starting off at a lower number than what typically happens in sustainability initiatives where they cost more upfront. So again, you have these really a situation where the water demand calculator broke the benefit cost calculation, which is kind of a funny piece. Diving into that energy bit, the energy savings piece a little bit more, I want to go back and reference one of the last times I presented for Coffee with Caleffi, specifically the 10 things to know about domestic hot water return design. We touched on the potential, the difference in terms of pipe sizing and the energy distribution from that. And if you want to learn more about how to size hot water systems, the return side especially, and how the energy losses go, I'll go back and feel free to watch the whole presentation. Definitely seems like a lot of folks have. Stealing one slide from there, I just want to point to, just kind of visualize that difference. So let's say you had a situation where you had normally you would have had a 4-inch water main coming into for a multifamily, let's say this was probably like 100 or 200 unit apartment complex. You had a central hot water system on the roof, which is very common for high-rise applications. That 4-inch hot water main, would have had about a 6.49, assuming, again, I'm just picking a number, not making a recommendation, just trying to show the difference here at the low end. So it would have had a 6.49 BTU per hour per foot heat loss, heat dissipation from that. And let's say using the water demand calculator for the supply side, you could have gone down to a 2-inch based on the parameters for this particular building. If you were to look at that difference, again, we're going to assume 500 feet of this. It might be more, might be less. Again, just trying to use some round numbers to give an example here. If you look at that difference, you're looking at about 10,000 MBH difference between one versus the other. So that equals about 2,000 US homes during the winter in terms of the energy difference and the energy savings there, just by right sizing within the building. So this is one area where, again, we want to do some more research, but there's an opportunity here by right sizing to have significant energy savings on your hot water side, especially as you start increasing the temperature, let's say, for things like waterborne pathogens. And that's kind of the next frontier of what we're going to be working at IAPMO, is looking at a paper to try to quantify some of the water quality improvement potential of right sizing, because one of the benefits, as Toju has mentioned, is that stagnation factor. By lowering it, you're certainly going to have lower flushing needs from a water management programming standpoint, but you also have that opportunity to just overall reduce the water age as your water is turning over more readily. So we're looking to get a report on that out here this year, hopefully. So again, there's construction cost savings, there's sustainability savings in terms of water and energy saved, and there's also that potential for improving water quality due to shorter water dwell times. And all these reports are available for free. Some of them are on our website. All those links are down there at the bottom. I was to say, Max, I'm not sure if you're going to get all those out there, but again, I think hopefully we can get to some of these, and all of them are available on that Water Demand Calculator website. We have links to all of them that you can freely access. So let's switch gears, and Toju and I will tag team this section here. So just, what's the next steps with the Water Demand Calculator? So one thing worth noting is that when you look at the smart building technology, SBT, usage in various commercial buildings, one of the big challenges right now is the fact that plumbing is basically at the rock bottom in terms of smart building technology usage, or even the potential plans for implementation. The Endeavor Media did a study back in 2022, and I had the privilege of being a co-panelist at the NIBS conference with Wanda Lau. And we talked about some of the latest things in terms of data and water usage inside buildings. She was with Endeavor Media at the time, and she was kind of presented these findings. And when you started looking at her slides, it was pretty a bit striking and not a good way for plumbing. She definitely shed a light on a problem. When it came to actually using smart building technology, plumbing was 16th place out of 18. And really, it was only 19% of the buildings currently were using any kind of smart building technology for plumbing systems. This was well short of this over 60% smart building technology utilization for HVAC and lighting. The plumbing smart building technology utilization was actually even lower than irrigation systems for things like residential, office, mixed use, and data centers. Only healthcare had a higher smart building technology usage, and that's where it slightly beat out irrigation. And then in terms of implementation plans in the future, only 8% of building owners surveyed planned on having smart building technology on their plumbing systems. There was almost 63% that had absolutely no current plans to install any kind of smart building technology utilization on their plumbing systems, which obviously includes hot water systems. So we had a huge shortfall in any kind of management. And so there really is a need for someone to go back and measure it, which is what IAPMO has been doing. So what the approach we've taken has been to work towards a general commercial calculator. Right now we're collecting a lot of data towards that. And as you can see here, our goal then is to start subsetting that data into different buckets. Now the data we need is there's three labels to it. First is macro data. Macro data is what we're determining as any kind of peak flow rate into, let's say, like from a water meter or the water supply coming into a building, or into a water heater and out of a water heater. When you're looking at multiple fixtures over a large portion of the building, we've kind of dubbed that as macro data. Micro data on the other hand, is when you start putting sensors on individual fixtures, on an individual shower, on an individual lavatory. That's what we're determining microdata. And so we're looking for macro and micro data opportunities. And Toju is going to touch on that here in just a moment, what we specifically need, especially on the macro data side. The third verbiage that you're going to hear us use is what's known as metadata. So we need a total list of plumbing fixtures. Anything downstream of that sensor, we need to know the type and the total number of those types. So for example, we need to know how many water closets, how many showers, how many lavatories, how many sinks, et cetera, et cetera. And all of that's key because we use that macro and micro data along with simulation of and looking at that metadata. So the simulation could be like an analysis, and that gets us to that water demand calculator, 3.0, if you will, for commercial buildings. And that's what we're working towards right now. So Toju, do you want to touch base real quickly on some of the specific needed data, especially the macro data when it comes to the water coming into a building or from a water heater?
Sure. So what IAPMO is doing right now is we're looking for people with buildings to give us access, and we can collect data. We know that collecting data at the individual fixtures is expensive and cumbersome, so we'll start with the water at the main, or if we're looking at only hot water use, after the hot water heater, and measure the total flow going into the building. We would need to monitor for 3 to 4 weeks. We'll prefer logging intervals below 60 seconds, and then we need to know number of fixtures in the building. And if we're looking for something like hotel office, we would like to see if the occupancy is affecting this peak water demand. At the moment, we need about 140 buildings per type to be 95% confident that we have a representative database, and that is what we're going for. So if you would like to partner with us, next. So what we're looking at right now is the type of data we would get looking at the flow going into the building, which is just total flow going into the building. This is from an office building. We can see little to no use over the weekends, and you can see peaks used during the weekdays. And what we will measure is this, and then we can work our way back and look at the water use in the building in different ways. Next. So on the left is the profile from the building, but we can turn that and look at it in a 24-hour profile to see when water is being used, or the different hours water is being used. The top plot is showing a building that had what we called a leak, and that's because something was on and running constantly. You can see that space at the bottom of the profile, and then you can see it when you're looking at the daily hourly profile on the right. You can see that all the high flows, but at the bottom one you can see the building is basically used every day, more like in sync. Low water use between midnight and 6 a.m., and then water use till the next midnight, which is the cycle for the building. So looking at the flows at the meter, we can see leaks if it's that obvious, and we can also see the way you're using water in the building. And with that, we can determine the peak hour of water use and try to estimate our probability values for the fixtures in that building based on that information. Next. Something else we can look at in our given our data is here we have the GPM, and then we're also looking at the probability of stagnation. And like we explained before, stagnation is when there's zero flow. The building on the top right-hand corner is an office building, and the lower left-hand corner is a hospital that had a water management program. And you could see that they were continuously running water to flush their system. And that we can see from the data we collected in their building. And we would either confirm what you are doing or let you know what's happening in your building based on the information and the data we collect. Next. For this next one, we're looking at water use in hotels, and this is for a presentation in the future, so you're getting sneak peek. What we see, there's on the left, we have 7 different hotels, and we've identified, you see all of them have similar peak hours of use, which is between 6 or 7 a.m. till noon. Some had extend, but if we pick the most used 3, it will be 9, 10, 11 a.m. in the morning. And they are separate because, well, because of the scale, the lower plot would have just been a straight line on the bottom of the plot. But you can see when water is being used. But on the right, we have summary of shower use in one hotel building with 40, we're looking at shower use in 40 guest rooms for 365 days. And on the average, we have each shower is about 10 minutes, 30 seconds, which is higher than single family residential buildings. From our previous study, that was about 8 minutes. But we see that in a hotel, people use water differently. You can see the maximum of 1,418 minutes. That's about over 23 hours. And water was running in a room. I cannot guess what the person was doing. But we did have 17 instances in over 3,000 data points that exceeded 60 minutes. And so we can see people's behavior in a hotel is different from as they will behave in their own homes. And these are the things that will inform us in getting those parameters necessary for the right set of buildings. Next.
Toju, I think that's a great point. And just worth noting, one of the things that, again, with the behavior portion of it, one of the things that is being thought of for the showers running so long, 8 hours, 24 hours, is in part people are using their bathrooms as steamers for their clothes. So one of those things that, as we've talked this through with various entities, that focus on hospitality, is, the questions arise: should guests be charged for water? Should there be some kind of shutoff for the water? At a certain point, is there a certain allotment that hotels should have per guest for their showers? So it starts, interestingly enough, we're starting to look at the behavioral usage and some of the behavior patterns in addition to just the engineering structural side of things. And so there's going to be some things to lean in on moving forward here in that as well.
Thanks, Christoph. One thing we also noticed that the peak shower use did not coincide with the building's peak water use. Shower use was mostly in the evening, but that's discussion for another day. Now, this is a summary of buildings that we have gotten so far. And there's a red triangle, which represents the average of the daily maximums, depending on how long we studied. So we studied for between 7 to 77 days at various sites. The green is from mercantiles. This is like the grocery stores. The blue in the middle is hotels. The white higher ed, those are university campuses. And the red is healthcare. Those are hospital buildings. And so we see the red, and then the black dot is what the design GPM that they had for the building based on the fixture details that we have. And you can see for the mercantile buildings towards the extreme left, there's a small difference, but that's because when you're looking at a very small building, there's not too much variability in your flows. But as the size of the building increases, number of fixture increases, that's when we see all the variabilities in the flows. And for the hospitals, there are a whole lot of fixtures that they are not even using. And so we can see that very great difference. But if you look at healthcare 8, you think, well, that's an anomaly. That was an outpatient. So it runs basically like an office. And you can see it's similar to the very last data point on the extreme right, which is also an office building. So these are just information we are getting based on the data telling us what is happening in the different buildings. And we are using all this information to see how we can get a simple, single water demand calculator version 3 that will apply to non-residential buildings.
Excellent. Great summary, Toju. And again, the peak flow rates there, that's the average daily maximum, which is also a higher number too than what the actual estimated 99th percentile peak flow rate was. Correct, Toju, if I recall correctly?
Yes.
Excellent. So just to kind of get here and wrap things up, we're going to go through these next few slides just a little bit quickly. If you have a building owner, or if you are a building owner, or if you're an engineer or installer, or even a code official, and you have maybe a recommendation for us to come in and collaborate on some of this research. I mean, obviously, when we have our sensors that we can loan out, or that we can look to have either our staff or volunteers install, there's some really great benefits in terms of any water savings or stagnation probabilities that we're able to determine. We have NDAs with a number of Fortune 500 companies already, but we're always looking for more. As Toju mentioned, we need like 140 buildings. So the more people we can get in, more building types we can get in there, we start really filling in this stuff. So it's definitely, it's going to take some time, but we're making some great strides here over this last year. If there is somebody that wants to collaborate with us, we have some templates, in terms of the building data that we need that Toju has created. We have some information we can share in terms of the benefits of collaborating. We would definitely welcome you. If you are interested, please go to our Innovation Task Group sign up. That's the QR code there in that website. Sign up for the Water Demand Calculator task group. We also have another one that Toju and I are overseeing, which is the hot water recirculation one. Separate topic, but also a good one. I think we have some folks from Caleffi on that particular task group, and certainly some folks probably even on the call today that are members of that. So just thank you on that. So just as we kind of roll through these last few slides here, just to provide some resources as we get to the Q&A, and Max, if you want to come back, we'll definitely can go through that Q&A here with the time. We have a few other pieces that we didn't touch on here today, but one was a white paper that we developed that talked about adaptive reuse of offices to multifamily residential. That's a free download, and we looked at, one of the things we looked at was the water demand calculator as part of that process, and the benefits, which really accounts for largely being able to reuse either water service mains, or even in some hotels that convert to adaptive reuse, you're able to reuse most of the system, as opposed to having to reroute new water mains and doing the demolition of work. So there's even more considerable cost savings there. Another one is the peak water demand study. The full study, we're very happy to report, is out as of last year. That is also a free download. Up until this point, we had the executive summary on our webpage, which we still have. That is also a free download, but you can go and download the full study to see how the math and everything that Toju did. And again, if you want more details on that, we have different pieces there, different videos we've done that have really dived into that. Also, Toju did a great job on a white paper that really touched on some of the anomalies that can occur from a simultaneous flow, especially as you're getting to some of a certain, I think it's the Hunter's curve number. When you're starting to get less into the modified Wistar method, there's that boundary there, Toju, if I recall correctly, that sometimes you can see that the water demand calculator so you'll start seeing an increase of flow rate as you start reducing the number of flow rates. And so we've gotten questions about that, and Toju does a great job explaining that in this particular white paper. And again, stay tuned. We have a whole research section on our IAPMO website. That's a QR code that'll take you there. We have a lot of white papers, these ones and others. We're going to be continually posting some of that. The water quality benefits of right sizing that we're working on right now, that'll be up there as well. Also worth noting, our Water Demand Calculator Summit, we've had our fourth one last year, the 2024. We have another one coming up here this November. And we're going to be sharing even more information. So if this is something you're interested in, you can get CEUs. We mentioned certain sponsors and people that have helped us as a thank you. It's a great opportunity to learn more about what we're doing in the realm of the Water Demand Calculator, especially what's coming up and what's happened over the past year. Also, we'd be remiss if we didn't also touch on a new tool we have for the Water Demand Calculator. So this does not replace the free tool that I mentioned before, but we do have a subscription-based WDC Pro that is, it's a subscription of $29 a month or $299 for the year. And in essence, this is a great tool that we developed to help augment the usage of the Water Demand Calculator for multifamily applications. One of the things we heard back from industry was it'd be really nice to have a tool that kind of helps speed up that process for multiple dwelling units. So if you want to go on the website and subscribe, or you're interested in learning more, please feel free to reach out to myself or Toju. Happy to give you some more information and collaborate. And we're looking at continually updating this tool as well as things move forward. But the idea is that you can create templates for different apartments and much more quickly run through your points of interest, your different pipe segments. Some of the folks that were our beta and Charlie and Delta testers, they were finding out that there was probably about a 50% time savings even over the normal water demand calculator, which was already faster than the Hunter's curve. So definitely some opportunities for further budget savings, on your budgets for your projects. And all of this is to say that when it comes to these kind of plumbing innovations, there's a great quote by Peter Drucker in his book on management, written back in 1974, almost getting up there in terms of the age of the Hunter's curve. But he noticed that because knowledge rapidly deteriorates unless it's used constantly within an organization or in an individual, you have to have somebody that's specialized and it's really doing this sort of stuff on a day-to-day basis. And the beautiful part about organizations like IAPMO or ASPE is that we are specialized in plumbing. We have an emphasis and focus on that, and that's where these kind of innovations like the water demand calculator comes from. So with that, we finished. I think about rough on time, but we definitely are happy to stick around for questions as much as we can and help provide some more context. And then definitely would love to hear if there's a subject that you guys, I know we kind of threw a lot of information at you, but if there's one that you guys want us to come back and focus on, we would definitely be happy to hear about. And I see the poll popping up, so definitely interested to see what people, if you can vote in that, would love to learn more about what you guys want to see.
Yeah, so I'll just kind of leave that up and we can do a couple questions here. This is the hardest I've worked on the back end to get all those links into the chat. And there are a lot of great resources there. And a lot of the questions that came in, I would say you would find a lot of the background in those reports and things that were mentioned there. So just if you're looking for more confidence based on a number of buildings or whatever, we're happy to follow up with the questions that we got through the chat. But some of those last slides that showed the different building styles that you're kind of expanding into with commercial and hospital and restaurants and hotels and things like that. We had questions about like, well, when are we going to get this type of building? Which is great. It's great news that people are asking for more kind of use cases. So I'm going to put you guys on the spot. Can we just have the water demand calculator 3 today? Do you have to launch? We'll take it.
That's a great question, Max. And we get that one often. And we really wish we could give it to everybody today. The problem is, and Toju, you could probably touch on the statistical technical portion of this, the reasoning behind it. But we really do need to focus on getting a high number of buildings. Again, 140 for just a general commercial calculator. And then eventually 140 of the subtypes that we've identified. And part of the reason for that, and Toju, feel free to chime in and add to my answer, is we need a statistical significant portion of buildings or statistical representation of buildings. Because if we don't, and we haven't accounted for those, there's the risk that we end up with a bad mixture of buildings that could lead to undersizing. And so we really do not want to do that as an organization. Obviously IAPMO has a wonderful name in industry. ASPE along with us, in terms of providing information that is usable, that is good information, and that people can have confidence in. So as far as that goes, we can't put something out there that doesn't have that hasn't gone through our own internal rigors as staff, but then B, it also has to go through a technical committee from an ANSI side before it can be an ANSI standard, and that's really an important piece to the development of these kind of tools, is that we need to make sure we also go through the ANSI process and have a balanced body look at this and verify and confirm and acknowledge that confirmation in a public way that this is good to use. So that said, we're trying to get there as fast as we possibly can on our side. So if that's where that part is where you all can really have an impact on this. If every single person on this call was able to get us one building, we would be there. That'd be amazing. So definitely don't discredit the fact that you can't get us a building. If it's your own engineering office building, that'd be wonderful. We're looking at hospitals, we're looking at schools, we're looking at hotels, retail spaces. All of these, as Toju, Dan, and I have collaborated on this topic. along with other experts in the field, we feel that those building types especially are going to have that lower likelihood of simultaneous use. As the chart that Toju showed, that's definitely being the case. Toju, anything you want to add as part of that answer about wanting a water demand calculator 3.0 right now?
Yeah, so as with general data, we want the results from the water demand calculator to be such that if you have one more building with a data point, it doesn't necessarily change the parameters that are in the water demand calculator. So that's why we need to collect as much. For the residential, 1,000 buildings was great. And so we know that even if you're bringing buildings that don't function like residential buildings that are complete outliers, the results will not change. So that's why we need more buildings.
Yeah, that was great. We had some other questions about just like, well, what about luxury hotels and things like that just might be an outlier compared to an airport, motel, two-story motel versus luxury vacation resort where people are going to have a very different shower potentially. But I think that's a great answer. That just the bigger sample size, the more confidence there is in that. So I'm going to end and share the results here. So it looks like how to use the water demand calculator to design multifamily projects was the slight winner there, but we can kind of look at that and type anything into the question pane that you want to address there. I have a ton of questions, so I'm going to see if I can consolidate a couple of them. One of the things I wanted to mention that we talked about, what's next, but I'm just going to I put in the chat the fact sheet for the water demand calculator, and there were some questions about where specifically, and I'm just going to do these really fast. So
sure.
California, Hawaii, Montana, Nevada, New Jersey, New Mexico, North Dakota, Oregon, Washington, and Wisconsin, and that's in the text of the fact sheet, as well as the 24 UPC that allows Appendix M different calculators. Is that a good way to summarize that?
So you got all the states, and then there's a few new ones that are popping up this year. So some examples are Minnesota and Iowa. The plumbing boards they're both voted to approve the water demand calculator as part of their update to the UPC, as both states adopt the UPC. I think you had mentioned New Jersey and Wisconsin. Those are two states that don't adopt the UPC. They have their own plumbing codes. Actually, it's 2 of 4 states that have their own homegrown plumbing code. But they also have the water demand calculator adopted. And then we have the city of Phoenix, where I live. They are looking to officially adopt the water demand calculator, which is wonderful news here in Arizona, because we have issues with the Colorado River and our water supply. So that's definitely going to not solve the problem. There's no silver bullet for that, but it's definitely going to help and be a positive in that regard. And then Castle Rock, Colorado actually became one of the first jurisdictions in Colorado to approve and mandate the use of the water demand calculator. So, and there's that was interesting because it came from their water department. And we've worked with a number of water departments, such as Portland and Charlotte, because there's different places that want to start using the water demand calculator. And that comes from AWWA Manual 22, M22, which revolves around water sizing and meter sizing. That document actually recommends the water demand calculator for the sizing of service mains and water meters for residential occupancy. So, and that kind of goes to the part that even if your state doesn't adopt the water demand calculator, there's still opportunities to use it. Some states like North Georgia, like the Atlanta metro area, the North Georgia Metropolitan Water District, Water Conservation District, they actually have allowed the water demand calculator, kind of circumventing the building officials there because they want to have every sort of opportunity to save water. The other one is other states, like if you live in a state that hasn't officially adopted it, you can always apply for an engineering variance. Some of the most early uses of the water demand calculator definitely fall in that bucket. So there's places like New York it's been used, in Texas, which every city has its own plumbing code, much like Arizona. We're kind of those two anomaly states that do it a little bit different. And other places across the country. So if you're doing a multifamily project, which is I imagine most of the folks on this call are probably looking at, there is going to be an opportunity. You just have to go through that variance. But if you're working with a code official and they have some questions about it, by all means, feel free to contact myself or Toju or Dan. But if you want to start with me, we can help you with potentially explaining the benefits of this and come in as a partner for adoption. And we have definitely volunteers and other advocates for the water demand calculator across the country that would definitely be happy to help step in. So hopefully that kind of gives a bit more context. But great summary, Max. Really appreciate it.
Yeah, and then one just a clarifying thing. When you said structural water waste, we had a question about that. Do you kind of want to give us a quick definition for what structural water waste would be?
So structural water waste is the difference in whatever volume you can save due to the design and installation of a piping system that serves something that utilizes hot water. If you can reduce that volume of designed piping, either by length or by diameter, that would be structural water waste. So, however, especially if you have a longer distance of piping, then you have the situation where that increases the volume. Behavioral water waste is that function of once that water reaches a bathing or usage temperature, like in a shower, let's say, and you don't start using it right at that moment. That's the behavioral portion of it, where somebody is not using it. And there's certainly devices out there. Some of those are actually in that We Stand document as well. That are there's IGC standards that can be referenced in engineering specifications to help try to eliminate that behavioral water waste. But the structural side is just the straight up design and installation, especially the design of length and diameter. If it's longer or larger than it needs to be, that contributes to structural water waste. Worth noting, the We Stand also has a provision in there now, the 2023, that's around hot water ratio. And I believe, if I recall the limit correctly, is if you were to draw a box around the hot water system, like a square box, to determine the area that it encompasses inside a building. Um, the We Stand actually indicates that box can be no more than 60% of the total area for the whole building. So let's say, as a simple example, if you had 1,000-foot home, that's the total square footage of the inside building footprint. The We Stand would say no more than 60% of the area, or 600 feet of that total, could have hot water in it. So that kind of gives you a quick example, and the idea being to shrink down the hot water distribution lengths to minimize that structural water waste. That's another method, along with the water demand calculator. Hopefully that kind of answers that question, Max. If you want a different piece of that, hopefully that gives a fuller answer there.
No, that was great. That was a great description. And then a couple other comments were about, well, we're going to need smaller pipe sizes. And I mean, that part, I used to work for Rayhow, a PEX manufacturer. Like, you can make smaller pipes. It's just how many people want 3/8 pipe. If that demand goes through the roof, then like it is technically very easy in the big scheme of things. And I think that the more people that are requesting, switching from 1/2 inch to 3/8 for the fixture runouts, that's, it is possible. We just would need more demand as an industry, I think, to get that on shelves everywhere. So it's easy for plumbers to pick up.
One little bit of nuance to that. So just keep in mind, the water demand calculator is looking at not necessarily the fixture runouts, but definitely what we're looking at is the potential in a branch that serves 2 or more fixtures, what that likelihood of simultaneous usage. So right now the model plumbing codes allow for no less than 1/2 inch for that. And so, really where you're starting to see some of the nuance, the 3/8, we're probably talking more typically the fixture branches is where some of the discussion lies, in whether that should be allowed or not. But especially as you're reducing your flow rates at an individual lavatory, let's say in certain places where it's gone from 0.5 down to 0.35 or even lower, that's where that discussion comes into play. But depending on which code you follow and what your local jurisdiction allows, 0.5 is generally, 1/2 inch is still the lowest you can go to. But switching back to that combined, the 2 or more, that's the water demand calculator. And what's interesting is, we had some concerns where, or some, worries that any kind of pipe manufacturer would have concerns about the water demand calculator, if there was going to be some resistance to utilizing the water demand calculator in multifamily. And what we've actually found is, if anything, there's just as much enthusiasm, if not more, from some of the various pipe material manufacturers, whether it's PEX or copper or CPVC or stainless steel or others. And we kind of asked them, like, aren't you concerned about your bottom line, like any kind of revenue loss? And actually what we heard back was very encouraging, which is, if we have a job site for like a 100 unit apartment complex, the total amount of piping we need for that hasn't really changed from the water demand calculator. In essence, we still have all the same lengths, but instead of having to supply to that particular job site pipe sizes from 1/2 inch to 4 inch, with the water demand calculator, we just have to supply pipe sizes 1/2 inch to 2 inch, and we might just have more of that 2 inch, 1.5 inch, 1.25 inch, 1 inch piping than what we would have had with the water supply fixture unit method, the Hunter's curve method. And the benefit, what they've shared with us, is multifold. One is it makes their whole process in developing the piping, the spools of piping or the lengths of piping much more efficient because they're just creating more of a certain pipe size. So there's economies of scale there. But the other part of it that they really like is that their shipping costs go down because it's less large pipes, so the weight goes down. And so they're actually able, on a dollar per unit basis, actually their revenue increases because their costs go down while they're at a much faster rate than what their revenue goes down. So they actually make more on those types of projects. So not to mention they're all, many of those are very pro the sustainability benefits of water and energy. So it's been really unique and interesting to kind of just hear that even some of these areas where we may be worried we're stepping on somebody's feet, that they're still very much pro the development of the water demand calculator into other spaces. So booster pump manufacturers are another one. Many of them are touting. We even had one out of California that put an advert in some of the plumbing industry magazines saying, we use the water demand calculator. It was kind of free marketing for us, but they were touting that as a benefit that they do because their pumps are more efficient. There's less change out of equipment. And they're able to go with better pumps and beat out some of their competition. So overall, the reception by the plumbing industry, from any angle, manufacturers, engineers, code officials, the installers, has been very positive towards the water demand calculator, which just goes to show that a lot of people are really excited about this 21st century development.
Yeah, and I can echo that just from like a simple example from Caleffi with mixing valves. The Our least favorite conversation to have on the tech support lines is to figure out that somebody has a 2-inch mixing valve when they needed a 1-inch mixing valve. And
Yeah.
while we would have made more money on that sale because they bought more brass from us, it isn't the best system, and it's not going to be the best valve for the project. We're more interested in getting it right so the system works well than we would rather downsize and get it right, essentially, as you're saying, kind of in those other examples. So it's been very helpful for us. And that's what, if we run into a case where somebody has no as-built and they're trying to figure out, what do I do now? This mixing valve is hunting. It's like, well, do a just sanity check with a water demand calculator, because you probably don't need that big a mixing valve just based on what you're telling me. And that's something that's been really useful for us on the tech support lines too. Like, no, we don't want you to buy a bigger mixing valve than is required. It won't help you.
Yeah.
So I think that there, just as we were answering those questions, we got some more. We'll do one more, and then we'll follow up with some of the other ones. I've got another kind of research question. So there was a question if the Energy Star portfolio manager benchmarking data is being used as a data set here. Is that something that, or it sounds like you've got something to say there?
Yeah, no, we've gotten asked that question a few times. So unfortunately, the Energy Star and most water meter and water utility information, it's not granular enough for us. If I were to go back to, and I'll see if I can go back to that slide to kind of share. Actually, let me pull back towards that one to answer this question. So give me just a second here, because this will give kind of a little bit of the answers for it. Perfect. Unfortunately, much of the Energy Star, that data, it tends to look at it day by day, or even some of the water purveyors get down to 15-minute increments for water usage. At best, is from what we've seen. We need to get less than 60-second increments. And really, when you start looking at the data itself, what you start noticing is that volumetric flow rate, and that a lot of the utilities and like Energy Star are looking at, versus what the peak flow rate are. And Toju, correct me if I'm wrong here, but they're a bit disjointed. They're not really the peak flow rate and the total volume usage. They're not necessarily in line. We've seen a lot of cases where the volumetric flow rate is highest on days that had lower water use for certain building types. It just kind of depends. Sometimes they do go up together, but not always. And so really we're looking at a data requirement of having something less than 60-second increments. And honestly, the data that we're looking for at best would be like 5-second increments, 2 to 5-second increments, which is very, very granular compared to what most of the water utilities are looking at. It's much more granular than what is out there, and that has been traditionally used by the water utilities. But that's what we do as professional engineers of mechanical plumbing systems. Basically, that's the level that we're looking at. And so it becomes a bit tricky when you're looking at these data sets, we've had to actually, we've looked through a lot of data sets. Toju, Dan, and I, we're looking under every rock. And that's why ultimately at APMO, we have sensors that we can loan out, and we're putting sensors in buildings, non-intrusive. You don't have to cut into pipe. They're mounted externally, but we've been using those types of sensors to get that data resolution that we need to making sure that the peak flow rates jive with the with the calculation tool. Toju, anything you want to add in terms of that, especially on the topic of peak flow rates versus highest water usage?
Not really. So what we're seeing is that some buildings might use water and spread it over time. And so there's just continuous use, and you see total volume of use is high, but because it's spread over time and it's not all stuck within 1 hour and there's no simultaneity, you don't have all the peaks that we think. And especially most of those buildings, like those 20 multifamily that we showed that used to adopt the California Energy Code, that study especially, you can see these buildings have 384 units and you're only seeing 20 GPM, and that will be from like 3 or 4 fixtures. So there's a whole lot happening, but it's because it's spread over time. We are not seeing the simultaneous use. And even when there is peak use, depending on how the fixture is being used, yes, there's a line of people waiting to use the fixture, but it doesn't mean that water is flowing at the fixture. So use, for example, halftime, the restroom, people occupy the stalls, but they're not flushing the entire 2 minutes or 1 minute they're there. They flush once, and that flush is for like 5 seconds. So that overlap, it has to be literally timed for most of them to overlap each other. So there's use, but it's the simultaneous use that we're trying to design for.
Yeah, and just while we're on this slide, I think there was one question that came in terms of like, how about the number of occupants? Especially like for hotels, or even hospitals, we are asking for census data if possible. Although, Toju, I think another thing that we found is that like in the hotels that we've looked at, is that the number of occupants, that there isn't necessarily as much of an impact on the peak flow rates as maybe what one would expect. Do you want to touch on that just real quick? Because I saw that question come up, and I think that's a good one to answer here.
Yeah, I saw the question. We're trying to see if the number of occupants is affecting the instantaneous peak. So far, the data doesn't say that. Number of occupants might increase the total volume of use, but not the instantaneous peak. There's no positive trend to that saying that right now. So we'll need more information.
Yep, definitely. And that's why we need that total number of buildings, as many as we need. So let me flip back to the last slide just for people that they want contact information. Anything else you want us to answer, Max, today?
I think that we'll have to get back for some of these more specific questions. So that's probably a good spot to call it. Really, really great presentation today, and helpful, because we get those questions that are kind of really how much do you trust it questions. And I think that you had a lot of great resources to show for people to kind of do additional research based on the links that we put in the chat. So thank you again. This was great. We'd love to have you back on. We'll kind of get back in touch with the survey results to see what the next topic would be. But yeah, thank you. And have a great day, everyone. We'll see you next month.